So last time we left off, we were talking about propagators. We'd worked through a fair bit of how propagators work. I don't think we'd really had a chance to really transfer any knowledge about how one kind of propagator, or one problem that happened to be a propagator problem, transfers knowledge to other propagator problems. So I should maybe do a bit about that. Then we can do a bit of a deep dive on unification modular group actions to reduce pressures on propagators. And then I think what I'm just going to do is the last hour of this, we'll just go through a bunch of code. Does that seem like a reasonable syllabus for the remainder? So the first example that we had that sort of sounded like a propagator problem was the SAT, solving SAT, where I had some conjunction of disjunctions of leaf level literals, x, y, not z. Okay, and the two sort of life lessons that we took here, or we took one life lesson from here, which was the notion of conflict-directed clause learning, and, well, we took unit propagation as well. But there's a third life lesson which was sort of important to actually make SAT practical back probably 25, 30 years ago in something called zchaff, which was the first engine that actually sort of got that story right. And they used a scheme called a two-watched literal scheme. Okay, and the idea was this. Let's envision this clause has 500 items. Every time I invalidate an item, I learn, well, x is not true. Well, that didn't make this one true. So let's scan through this whole list and see if I am down to one item. And then I would invalidate this one. Well, y is not true. Like, let's say there were a lot more. I'm going to keep doing this. I'm going to wake up and go, oh, well, maybe I can propagate like 499 times before I actually finally propagate. So the idea of a two-watch literal scheme is actually kind of clever, I think. Like we established before that if you had 0 items in a clause, if you had 0 literals left in a clause, we would blow up the universe. If you had 1 literal left in a clause, we would propagate. So in any stable state, you have at least 2 literals in the clause. Okay, and until you're down to 1, you don't want to propagate. So pick 2 of the literals that still do not have a value assigned to them, any 2, and watch those. Because until I write to one of those 2 literals, it is not possible for me to be down to 1 literal left to work with. So only wake up on 2 of the literals. And then when one of those changes, go scan through and continue looking to see if there's anybody else who you could watch instead. And watch that one for that literal, or unit propagate. The nice thing about this is when you backtrack, you do not have to undo which of the 2 literals you're watching. You just leave this thing because you're still in a valid 2-watch literal state, even though you're watching completely different literals. So you only need to backtrack to control the overall thing. So this reduces the amount of wake-ups that we do for changes in our propagator network. And so I'm looking for ways that I can reduce the pressure on the propagator network. This is one of the most significant tools. And all we needed to know was, this is more or less about strictness. If you have it, we can look for things that actually act like one-watched literal schemes for other propagators when the propagator is strict. And what I mean by that is this. If we know that f of bottom is bottom, then until I've got an assignment to this input, there's no point in me waking up and doing this propagator if I'm strict in all of my arguments. So what I can do is I can watch a single literal, a single argument to my propagator, and wait for it to become non-bottom before moving on to watch the next argument to my propagator, and then continue to sweep through in this fashion until all of my arguments have woken up. And now my propagator should actually start firing on every change. But until at least all of its inputs are non-bottom, I shouldn't wake up. This assumes that your propagator takes bottoms to bottoms. But many propagators will actually be strict in this fashion. If I take a simple example, we talked briefly the other day about the fact that I could take the very simple like promise style propagators where I have a bottom level, which is like I just have bottom. And then I have values of, like -1, 0, 1, 2, 3, da, 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 da. And I have a top level, which is I blow up the universe whenever you tell me that it's both 2 and 4. And then, again, so for those of you who are just joining us, I hope you're comfortable with some order theory. Basically, a propagator to me is a monotone function between joined semilattices. That was mostly for Chris.
So if you join any of those middle elements, then you end up back at bottom. Or
You wind up at the top, and then we blow up the universe.
okay.
And then monotone function. So if you give me some answer for bottom, you can only give me something that's at least as defined for.
Okay. And if you stay at bottom, then you haven't proved anything.
But that's okay. And so the idea is, like, if I just wanted to do addition on 2 of these, it'll take bottom to the. We're going to be strict in both arguments. We only give non-bottom answers for when both of my arguments are non-bottom, and then I produce the sum. Okay, so that function, let's say I was doing addition on 500 arguments to produce a 501st, what I should do is scan through the just block, watch, pick one of my arguments at random, whatever you want to do, whatever scheme you want to pick, watch that argument. Until that argument moves to non-bottom, there's no way that my function, which is just going to compute additions on these arguments, will actually yield any answers. So let's keep waiting there, then move on the moment it becomes non-bottom, continue to scan until all of my arguments are non-bottom, and then propagate in the usual fashion. This is a sort of slow wake-up scheme that I like. I have another scheme for slow, slowly putting the propagator to bed. How to delete propagators from the network. When can a propagator no longer have any effect? So if, we have this top element here with this contradiction node that sits above above all of the elements of my lattice. So we need to talk a bit about what it means to be covered by something. So I'll say X is covered by Y using this funny symbol if there does not exist a Z such that X is strictly less than Z, which is strictly less than Y. If there's no elements in the middle between X and Y, X is covered by Y. Okay, so this is like, you can't go uphill and get to Y from X without having to go straight from X to Y. There's no intermediate step.
So you have nothing proved in the middle.
Yeah, this is usually used when describing how to draw like a Haas diagram for some order. A Haas diagram is those little, hey, I've got, I don't know, all of the ways that I can draw my cube or something like that, where down here I've got the empty set, and here I've got the set of X, and here I've got the set of Y, the set of Z, and here is, I don't know, I'd have to do this better. This should be Y. And this is X, Y, and this is Y, Z, and this is X, Y, Z, and all this stuff over here, right? Yeah. And so we've done set union to climb this joined semilattice in this case. But every element here, there's no element between the empty set and the set that contains Z. There's no element between the empty set, or between the set that contains Z and the one that contains Y and Z, etc. So each of the edges that we drew here were covers. An example of a place where you can't draw covers would be something like, I'm going to take the intervals of the rationals with intersection, and I can start talking about at the bottom, I have minus infinity to infinity, and at the top I have the empty set. Immediately below this, covering this covers each of the individual rationals. But then every level below that, it's not actually possible for me to find anything that has this property. So there's the actual points here, but then down here, this is this big infinite mess. So I can't really draw a Haas diagram of that particular. Well, I can't find anything for which this relationship holds. So this just basically avoids me drawing all these redundant edges here, where I have to connect everything to everything somehow. Okay, so what we were doing before was looking for places where we were all, that everybody had to not be bottom. We were strict. But a more generally applicable scheme is if all of our inputs to the propagator are covered by the top maximal element, the one that if you increase my input, I blow up the universe, then this propagator can never fire again, because any attempt to cause me to fire would blow up the universe first. So this is another scheme by which I can do less firing of propagators. Or in this case, I can garbage collect the propagator from the network. If all of the inputs of the propagator are sort of maximal in this sense, that they can't be increased without blowing up the universe, I'll throw the propagator away. So these two schemes are what happens in a SAT solver in disguise, because a SAT solver is working with a very simple lattice. Bottom goes to true or false, goes to contradiction up here. So the moment you learn the value of a variable, we are immediately in a state where that variable can't progress anymore. And we move on with our business.
So what does that define the behavior of having 0 propagators left? Does that mean you've solved your system?
Well, if you have no propagators left, there's going to be no propagation, yes. It's not the only way in which you get to quiescence. Basically, the idea is I have a lattice, I have a hypergraph, basically, where I've got, at my nodes, we have joined semilattices, and then I have the monotone functions between them as the hyperedges in this graph. I can have multiple inputs, that's why they're hyperedges. And whenever I gain input or information about one of the nodes, what I have to do is cause all of the outbound propagators to eventually fire. And then in the previous session, we started to cover conditions under which that are sufficient for this to terminate and yield a deterministic answer regardless of scheduling strategy. So this is the first life lesson I like to steal across domains, which is stealing the notion of like a K-watch literal scheme from SAT. Now, if I were dealing with 500 numbers and wiring them up with addition, I could actually think of one of them as kind of marked special, because this one's got its sign flipped. Everybody else is different. And then I could use a 2-watch literal scheme, because I can, if I have given 499 of them, I can determine the 500th. Right?
I'm missing that.
Let's say I was doing interval arithmetic. Okay. You give me all of the numbers, and I'm saying x1 plus x2 plus equals y.
Oh, okay, sure.
We've got x, 499 here. So if you give me all of the inputs, I can give you y. But if I give you all but one of the inputs and y, I can tell you one of the others.
Sure.
So you can do this interval arithmetic trick as long as 499 of my inputs are non-bottom. And so this goes back to being a 2-watch literal scheme, exactly like SAT, except for the fact that we wake up the moment we go to non-bottom on the interval arithmetic case, but we don't go to sleep until everybody's an actual concrete rational. Because now we are covered by top. And you can't go any higher without, So you probably don't go to sleep in that case, but you at least get to slow the wake up of the propagator. Okay, so I use this K-watch literal scheme to reduce the pressure on the propagator network. Let's go look at another propagator domain for a little bit, and then I think we'll put propagators to bed for a while. So the second domain I like to steal things from for propagators, that I think is pretty accessible, is the notion of data log. So in data log, for those of you who are not so logic programming inclined, I'm going to have the ability to create tables, which are going to look like prolog function things. And I'm going to be able to create relations between them that's going to look like a table join and then dump the input into one of these tables. So what I might have is if I had some kind of parent relationship, parent Bob, Nancy, parent Nancy, Dave, what I could do is try and compute like the transitive closure of this database and like build the ancestor relationship or something like that. If you modify this, you can start talking about shortest paths through networks. You can turn this into routing protocols. You can do all sorts of things like transitive closure is a useful property. Most of SQL 99 was them getting jealous of Datalog and building common table expressions to handle a few special cases out of what Datalog could do. So I build a couple of rules. I'll say like, you know, X is the ancestor of Z, given, I don't know, X is the ancestor of Y, and Y is the ancestor of Z. So we've got a transitivity condition here. And I could say, well, X is the ancestor of Y if parent of X, Y. So I write these clauses down. They're not ordered. And what this should do is I should be willing to, like, think of this as a propagator. Each of these rules down here is a propagator that's going to take the data that's in the tables that I have here, join it together, and write the data into the target table. So my tables are joined semilattices in the sense that I will use like the natural key on the table. So they just, all of the fields are part of the key. And I will produce the result. In this case, I'm just going to join on Y and write the answer into the ancestor table, which will add more rows. As I add more rows, all of the outbound propagators, in this case that read from the ancestor table, or in this case that read from the parent table, will fire and push all their values around. This would be naive evaluation of Datalog. No one's evaluated Datalog this way outside of a freshman class or something like that since Dirt. But it's a start. So I want to take this idea and like poke at it a bit and see what people actually do to run Datalog and see how I can transfer that to talk about other propagator problems.
So what does it look like in a system like this to, for instance, when you said if you join your semi-lattice and you end up back at the bottom again, or you blow up the world?
No. You only go up. You don't go down.
So what does it mean to join and go up and blow up the world in a system like this?
So in this case, we don't like the top of the. We never actually hit this contradiction state.
Okay, good. Yeah.
There's no top to this lattice.
Right. Anyway,
What we had an example on the first day of like the integers with maximum. Like we start at 0 and we keep going up.
So could we define that, you know, if X is an ancestor of Y, then Y can't be an ancestor of X, and that would introduce that?
You could introduce that. I think that's a different dimension on which you would have the cycle.
Okay.
This is actually going to be perfectly okay with those like you're your own grandpa kind of. You know, I've forgotten the All You Zombies Heinlein novel that has that as a thing. Like it could type check that hierarchy, or like it could deal with that relationship now. So Bob, Nancy, Dave, these set of relationships. So what do we need to do this better? Okay, so doing this full join is actually really expensive. I'm joining the entire ancestor table against the entire ancestor table. Envision I have 1 billion ancestor, and I've given you 5 new facts. Okay, so one of the techniques is something called semi-naive evaluation of Datalog, and there's 2 pieces that kind of happen in it. One of them is sort of rewriting these rules to say, well, what are the changes in the table since the last time I fired? And to kind of put this in sort of my goofy notation, I want to think like the delta or the nabla, I've got here in like time n+1 for A, for the ancestor table, from X to Z, is going to, if I make up some notation here, it's going to be based on the delta at time n, ancestor XY, joined against the full ancestor table from Y to Z, and then like some sort of plus, whatever we want to do here. The ancestor table at XY joined against the delta table for ancestor YZ plus the deltas at both of these times lots.
You only have to do the new joins.
Yes, and so now I join the small table against the large table, the large table against the small table, and then the small tables against each other. And we never do a billion entries against a billion entries. Do a billion entries against 5, 5 against a billion, and then 5 against 5.
Which is still bad, but better.
It's still better. Because doing the billion against the billion was the thing that was going to kill us. So now we need this notion of what is the delta? What is the change in my joined semilattice? I was here in the joined semilattice, and then someone drove me up to here. I want a description of, like the shortest description of this, like the added rows in the data log sense. Okay, so I have like some kind of commutative monoid that is acting on my partial order, that is the thing that comes from my joined semilattice. This is rather similar to the commutative replicated data types kind of story, where you talk about the message that has been received or something like that, rather than the joined semilattice or some joined semilattice that you would talk about in a convergent replicated data type, if that term means anything to people who care about CRDTs in the audience.
So could you think of your commutative monoid as the set of all rows in the ancestor relation database?
Yes.
Okay.
Well, the baseline, the joined semilattice is the set of all rows in it. The change since we last wrote, basically what I have is my propagator is sort of keeping track of a timestamp or something like that of like, what is the last row number that was in this table before I fired last time? What are the rows that have been added to this table since? So it's just the delta, the change, because like this is the smallest thing that I could join against the previous value of the joined semilattice to get to this new state. And if I can make a propagator that sort of keeps track of like this sort of log of the previous state or like a cursor into its state, and then I advance the cursor when I fire the propagator again. This sort of removes a bit of the pressure on idempotence. We now rely on receiving the message once, which is, again, the commutative replicated data type story rather than the convergent replicated data type story. So up until now, I've been using a joined semilattice. Now I just have sort of a partial order and the fact that each propagator will only receive each change to the input once. So we're getting away from it being a lattice variable, which is something that Lindsay did towards the latter part of her thesis. So I don't really think of LVARs and LVISH as really being lattice variables. They're Lindsay variables. Because...
So, sorry, what was the thing that makes it not behave like a lattice?
Because if I don't need idempotence if I only receive each change one time. So I have an order, and I'm going to make a series of monotone changes to the order. Okay, but if each propagator receives each change independently, then this is we're relying on guaranteed message delivery, not on idempotence to keep everything safe. And so in the CRDT world, there's two styles of CRDT, and they both share the acronym, even though they work differently. There's convergent replicated data types, which rely on a joined semilattice. And then there's commutative replicated data types that rely on guaranteed message delivery. And this is showing that we could use either style. And the commutative replicated data types are actually somewhat useful because, like, if you wanted to just keep track of like a bump counter or something like that, and store it as a single number, that is not a joined semilattice that I could really use. Like the only thing I can do there is max. Whereas if I want to allocate a fresh ID or something like that sort of thing is more like I need the guaranteed message delivery, that I only bump it for each client one time.
So you're kind of moving the idempotence from the actual merging of the data into the delivery.
Yes, into the delivery to each propagator.
Yeah.
So it's a different scheme. But this notion of finding a delta for your order or your joined semilattice is a recurring theme for me. Because usually these have a pretty short description. And I have some machinery that's in the code that we might get a chance to browse through, where I maintain like a set of fingers into a log. Like this is like a finger tree, where at various positions in the finger tree I have fingers. And if I have multiple fingers, this is like still a shared finger. And then what I'll do is there's the monoid from here to here, the monoid from here to here, the monoid from here to here. And then I can advance the finger to the front of this thing and grab this value, and it will expire the old cursor, moving it to the head, collapsing neighbor monoids, etc. So this is actually efficient in terms of the number of distinct locations that we happen to have fingers.
Okay, so you're using kind of a product of monoids where one of them is like the last monoid over the cursor, and then the other one is the...
No, I've got a cursor. A cursor itself is this mutable mess, right? We are in a world where I actually do have references and non-determinism. Okay. So and then, so a cursor is maintained as a reference to this thing that talks about, given the finger tree that I have here that's hiding behind a reference. Okay. Like, I'm at this position. How do I advance me and get my value? Yep. And so when I run the propagator, it's given, it can read its value and advance its cursor.
Okay. And then you only need to get the monoid aggregation up till the last cursor when you're...
Yeah, it's like from the last cursor, this is where I'm at, and it advances the cursor, so I can't ask that about that cursor position again. Sure. I'll only see fresh values. So that's what my log machinery, there's a log module that's buried inside a Guanxi that does this. So that captures one of the life lessons from Datalog. The other life lessons from Datalog is that I can topologically sort this network if we write down these rules as number 1 and number 2. So now I have, it's a hypergraph because I'm like reading from A twice or something like that. If this was, say, the parent table, this would compute the same answer, just less efficiently. Now these are parents. But we could sort of build a graph that is 1 and 2, ancestor and parent. Like you can treat a hypergraph as a bipartite graph where we just have edges between the, in this case, the nodes in my graph, and these are my edges, my hyperedges in my graph. And so I can say I have an edge from A and P into 1, and an edge out from 1 to ancestor, right? And an edge into rule 2 from P, and an edge out from rule 2 into ancestor. And if I take this thing up and I shake it and try and hold it in topological order, what this will tell me is that there's a strongly connected component here. But if I start from the parent table, I can feed rule 2, and then I'm done with rule 2. Unless the parent table changes, there's no more information that's going to go through this rule. So we are done with rule 2. Now just spin on this thing, firing this rule over and over again until it quiesces. So you execute your strongly connected components in topological order. And what this will do is give me the largest possible deltas rather than giving lots of small deltas.
So you're kind of trying to reduce the amount of stuff that you have to spin on until you reach a fixed point?
Yes. Okay. So the goal of this is, I said before that under lots of different conditions that I can find that are sufficient, we will terminate and yield a deterministic answer under all scheduling strategies. Now what I'm looking for is a good scheduling strategy, regardless of that previous fact, because I can still reduce the amount of work as long as I have some notion of delta, some kind of, like if we're working in this more commutative replicated data type style. Okay, so these are like 2 of the kinds of results that I got out of actually starting to think about propagators as a framework for transfer of knowledge from different domains. There's others. I think these 2 are like, these are the biggest impact ones. Okay. How are we doing on time today for this block? 20 more minutes for this? Good. That should be enough to cover group actions. So let's switch to code for a while, and then we'll come back to the whiteboard, maybe. So I'm just going to write a, is that big enough for everybody? Am I off the screen? I'm off the screen. Is that better? Sweet. All right, so what is a group action? Or let's start with monoid actions, and we'll get to group actions really quickly. A monoid action would be something like this. This is why I don't write this as a class. I'd have a monoid action class that is like some monoid acting on a set.
This is the update monad, basically?
Update monads use them.
Yeah, okay.
And then I would have some act, which takes M to functions from S to S. And what are the conditions that we want on this? We want act of mempty should be the identity function. And act of M append N should be act M dot act N. So we take the monoid, the append of the thing to dot, and we take the unit of this thing to identity. This is the monoid action stuff that I have. Now I will typically build this thing as a backpack module that picks a monoid. I'll lock down M and like bury that in a module signature, because that takes me from this being a multi-parameter type class to locking M. And now type inference works. Previously, this was going to be this completely undirected mess because you can't put a fundep on this thing. Making it a separate class per monoid actually like admits me a lot of power. Okay, so in the Coda code base, I do this for like a data type I just call delta in this case, and it starts off. Let's just lock this to the integers. Right? And to make this the particular thing I have there, I'm going to screw with everybody else who is handwriting this. Sorry. We're going to work with that. Okay? Okay, and so now we can say things like instance relative delta, where rel equals the, and I didn't actually write down the monoid. That's why I drive the num.
So you're defining a relation between delta.
I'm defining the integers, yeah.
Okay.
And then delta is itself, it acts on itself. And I'm generally, I use this thing a lot, so I'm going to just kind of poke at some uses for like trying to efficiently work with group actions. And then we'll actually get to some applications to union find. So I would like to have something like this. Well, let's actually build like another data type that actually uses this, like data error.
Do you get anything special from defining a monoid action where delta acts on itself rather than just using delta as a monoid on its own?
No, not really. I'm just using it as a base case for a bunch of things. It'll actually work. It works out nicely when you actually start doing GHC generics for this sort of thing. So it's sort of a base case for like constructing a larger thing. Like if I say error delta string or something like that, where instance relative error.
And you can combine your deltas and then run your deltas on your string.
But it's more if this is defined as a base case, that char itself, like the action of rel on char is nothing, then the action of char on the action of rel on list would of chars would be nothing, but then the action of delta on delta would actually be to act here, right? And so like it gives me a base case for GHC generics in the real version of this. So this is going to be an error d append d prime s. Okay, and I like this. I can now start talking about, in this case, we're doing the world's crappiest changes in file positions. I'm talking about file positions as number of bytes since the beginning of the file, right? Then, like, to convert back and forth between, like, I'm using this because it forms a group, which will help me later. I could use a monoid, which is the position monoid or something like that. Position is two integers. One is the line number, one is the column number, or something like that. And I come up with a semi-group for position where, I don't know, pos AB, pos 0D is like pos A, B plus D, pos A, B, or A. I don't care about your old column because I've now got a new column because I've got A, B, C, or I should have chosen a different letter, A, C, D. I chose these things consistently in the first place. A plus C, D. Right, this would be a, like, if I see a carriage return, it counts as a new line, but then I throw away the old column number or something like that. But this is only a monoid, whereas this is a group. And I'm going to want more group action toys later. So this pos monoid is useful. It's just not useful enough for me to use it as the way I carry everything around. Besides, I was able to describe the same amount of information here. It's just now if you get an error message, the error message tells you 538 bytes into your file, there was a problem. And that's not terribly useful. But if I gave you like a finger tree of where the line endings were or something like that, you can convert back and forth in log time.
Right, using a rope or something.
Yeah, so you use a rope or something like that, and you can convert back and forth in log time. So it doesn't really matter if I internally use the one.
Right.
And it lets me have a group, and the group will matter. Okay, so why do I care about this? In some of the Coda code, I am trying to parse monoidally there, and I'm like trying to reproduce syntax trees and like slightly modified syntax trees as you make small edits to the source file in roughly polylog-ish time. And I lose that game if I have to rebuild the entire syntax tree. I cannot rebuild the entire syntax tree with positions in it and pass that test, because it would be linear in the amount of time, or the amount of stuff I've touched. So I've already lost.
And you also don't know whether they added a new line or not, and then that offsets.
Yes. So how do I make it so that I can give you a new syntax tree? Or even like a list of errors. If the list of errors could be linear in the length of my program, the moment I go to write this instance will be indicative of the problem here. Relative A, relative list of A. I mean, it's an easy instance to write. But this is ON in the length of the list. Also, I don't really want to use lists of errors as my monoid, because the cost of a list append is linear in the length of the left list. So we'll actually be like quadratic in the size of my program if I'm just like folding up in a finger tree some list of errors. So I can't do that either.
So you're not using a finger tree then?
Let's say I'm using a finger tree of lines or something like that, and then I'm feeding it to my parser per line, and then lexing my way up.
Group, then you can use a finger tree.
So I'm just saying that this monoid screws me.
It's no good. Okay.
So I need to keep, or this monoid action is bad for me. So we first need to get to a better list. Okay? I want a list that I can relocate in O1, and then we'll deal with the appending problem independently.
Okay. Sounds good.
So the first trick, I usually have people do this with me, but let's just do it now. I can start with nil, which is okay, or const of A onto list of A. This is what we started with. Now we'll like use a variant of the sort of Koyaneta trick of, here is a delta that I want to have act on each of these things. And now what I'm going to do is, like, this delta applies to not just this node, but everything to the right of it, further on in the list.
Is that multiplied?
No, this is going to be, it's going to just be an append.
Okay.
So rel d nil is nil. Rel d const d prime AAs is const d append d prime AAs. This is clearly a 1 now. Const is something like const mempty. That's okay.
Okay.
Unconst.
So you're still keeping the sub-deltas, but you're keeping the sum of them at the top?
Nope.
No? I missed it.
No, all I did was I changed the top one
Oh,
here.
you only changed the top one. Oh, I see. Okay.
I haven't percolated it down through the list. This was, I made relative O1 by the change of by the cost of basically not doing anything. Unconst already had to do O1 work. So now I can afford to charge O1 work items during discharge. I can do O1 relocations in unconst. So let's look at what unconst should do. Unconst of nil is nothing. Done. Unconst of, let me get some space here. Unconst of const DAAs is what? This is just something. So what do I have to give back?
Well, you have to measure the A and undo the delta?
No, I don't need to undo the delta. I never applied the delta to the A.
Oh, okay.
I need to push the delta into the A. I'm pulling it out now. It should have been shifted. Up here, the head was going to be shifted when I did this action. I haven't done it yet.
Okay.
So I should relocate by delta A. And then I've got the tail, which I can relocate in O1 time as well.
So we can imagine that the A's here are the errors, is that?
This is going to be a list of errors.
Okay.
And I now want to be able to relocate the entire list of, a huge list of errors in O1 time. And now const is still O1. Unconst is still O1, but now needs a relative constraint.
Okay, gotcha.
Okay?
So you're keeping the offset kind of at the top of the list, and then when you unconst, you apply it to the one element that you're pulling out. But you
Yes.
keep everything else the same.
And I push it down. I push the delta down, so it merges. I merge my current delta into the next delta.
Okay, makes sense.
So each step is, I'm doing one step worth of work. Now this works for any algebraic data type. You have your syntax tree for your programming language. I put a delta in each node. And then the act of accessing the outermost constructor should push the delta down. Now that sounds tedious, so what you do is you maybe bury it behind smart constructors. You build pattern synonyms that like just hide the delta from you. You never even see that I had the deltas. But now I can build the syntax tree and I can relocate it in one time.
Cool. And you need delta to be strict, so you don't.
I want delta to be strict so that you don't build up a func there. But the nice thing, so when I'm looking at this is sort of like the Koyoneta trick, if you're familiar with that idea of like if I want to make a, I don't know, I have a data token a where token is a, I don't know, I take a char and I give you a token char. Like you might use this as like the base for a free monad or something like that. If I want this to actually be a functor, what I can do is I can sort of take char to a as an extra member here and build this. Now this is actually a functor where the previous GADT was not. I'm doing the same sort of thing here, but now the action that I'm supplying you is packed up as a delta, because remember, delta is really a function in disguise.
Okay, and that's just easier to work with, right?
Yeah, well, no, the reason that I work with delta is because when I append to deltas, I'm actually composing functions, but they're staying in a normal form that's not like a long chain of functions.
Right.
So the idea is like if I do rel and then rel again, it's still the same price for me to unpack.
So this is kind of a motivation behind monoid actions
Rather than just using a function. If I just used a function, then the composition of these things would actually be like linear in the total number of operations I did.
Gotcha.
Now we collapse them. So it like lets me sort of defunctionalize in a way that has a nice normal form. Cool? So this worked for any monoid. If I have a group, I can do better. So let's improve on this list and make it take less space by exploiting the power of a group. So now I want a list to be a delta. Anyway, let's make that strict and unpack it. No one in the audience cares, but I do.
This is a demo.
So now I want a relative list. Just like before. And by the way, usually I would have some kind of clause like rel by mempty, 0 in this case. Should be x's, and that way I get more sharing, but I'm, being a little glib. The unpack doesn't say that, but to me I am. So now what we have is something like this. I want unconst. Let's look at unconst again. Relative a, list of a to maybe a list of a. This is kind of similar to what we had up here. But now we have like lists something. Empty list is nothing. List D, a constant to a's. So we're still going to do this rel D on the A, but now this is just list D, A's. Okay, so unconst didn't really change much. But const has a new problem. I have an A and a list of A. I need to give you a list of A. So I've got an A and a list D A's. I need to build a list D something constant to A's. What do I do? Because when I take this element, I can't just put A here. So when I take it out, it's going to be relocated by delta. I don't want it to be relocated by delta. I want it to be relocated by nothing. So how do I put it back? How do I force it to not be relocated?
You do the inverse of delta.
Yep. So I can relocate by, I'm going to use my num as a shitty group for right now. Because I didn't want to write a group class. But like read that as inverse. Cool? now what we've done is instead of having 1 delta per const, I have 1 delta per list. So we've reduced the memory pressure, like just the footprint of this by a good deal. So now we have a list that has O1 rel and O1 overhead in terms of storage to actually get my monoid. It turns out there's a bunch of groups that I actually care about using this for, not just like the integers with addition. Examples would be finitely generated permutations of the naturals are good for talking about nominal sets. So I talk about permutations acting on terms, and I can make terms where I'm slowly doing the nominal set substitutions through the syntax trees. I have other ones for doing like actual honest-to-God substitutions.
So that's for guaranteeing using free names that don't conflict with
Yes,
one.
and I have other ones that can deal with things like doing like substitutions slowly through a syntax tree, which gets me the power of explicit substitutions. There, my monoids are no longer O1 in cost, but they're morally cheaper than doing the substitution yourself, which can kind of reduce the pressure on like de Bruijn-like things. And if you look at it like through the filter of those smart constructors, it looks like you worked with de Bruijn indexes, even though you paid less, because we were working with mergeable explicit substitutions. And we're at time or almost out? Okay. All right, then we'll pick up with using these group actions on like modifying union find with it, and then we'll do a deep dive on code for the last hour. All right, I think we'll break there.